This video goes over optimization using calculus. There are lots of different optimization problems, but the procedure is the same for each type. So this video goes over 2 types of optimization examples, and there are a couple more in your textbook, and you could research a few more if you wanted to, but these are our main 4 steps here. So assign variables to the known quantities and the quantities to be determined. If possible, you want to draw a sketch. You're going to write the equation to be optimized in terms of one variable. So usually you have some sort of constraint. Then you're going to take the derivative and set it equal to 0 to find the critical points of the function. Right? So this is f prime of x equal to 0. That's what you're solving. And then you're going to examine the critical points to see which ones make sense for the problem. And then you're just going to check your answer by verifying that you actually do have a maximum or a minimum. So the first one that we're going to look at is a fence problem. You have 102 meters of fencing to make 2 side-by-side enclosures as shown. What is the maximum area? So let's call this distance here the length, and then these 3 the width. So this is the length 2. So I'm going to define those variables. So let's let L represent the length of the enclosure. Let W represent the width of the enclosure. And we're going to let A represent the area. So this is my first one. Now I'm going to work on writing my equation to be optimized in terms of one variable. So I know that the amount of fencing that I have is 102 meters. So 2L plus 3W has to equal 102. That would be my perimeter. I also know that the area is length times width. So in order to get my area expression into one variable, I'm going to rearrange my constraint equation here for L. So I get 2L equals 102 minus 3W. Dividing everything by 2 gives me L equals 51 minus 3 over 2W. Then what I can do is I can take this expression for L, substitute it into my area equation to get the equation that I'm trying to optimize, all in terms of one variable, in terms of W. So when I expand that, now I've got 51W minus 3 over 2W squared, and then I'm going to move on to step 3. So I'm going to take the derivative, set it equal to 0, and find the critical points. So A prime is 51 minus 3W, setting that equal to 0 allows me to solve for W. So I get minus 3W equals minus 51, which is going to tell me that W equals 17. So I only get one critical point, so that must be my only option there. Now I'm going to verify. So if this width gives a maximum in my area function, my second derivative evaluated at 17 should be less than 0. This is my second derivative test. Okay, my second derivative is actually just minus 3. So that means that my second derivative evaluated at 17 is just minus 3, which is less than 0. Therefore, W equals 17 is a maximum. Now the question didn't ask me just to find W, so I do actually have to answer the question. I'm going to do that just step number 5 here. We're answering the question. So I'm looking for the maximum area. I know that W is 17. I also know that the length is 51 minus 3 over 2 times W. So I can solve for L by substituting in 17. Using my calculator or my brain, that's going to give me 25.5 meters. And then I can figure out the maximum area by multiplying those two dimensions together. 17 times 25.5, which is going to give me 433.5 meters squared. And then my conclusion is that the maximum area is 433.5 meters squared. The second example that we're going to take a look at is minimizing costs. So here we have a cylinder-shaped can that needs to be constructed to hold 300 cubic centimeters. So this is our volume of soup. The material for the sides of the can are $0.04, okay, or 4 cents per centimeter squared. And then the top and the bottom is 5 cents. So first thing that we're going to need to do is define our variables. So if I draw a sketch of our can over here, I'm going to let R represent the radius. I'm going to let H represent the height. I'll let C represent the cost. And I may as well, I'll write down V too. Let V represent the volume. So I'm just describing everything that I'm using. So I know that my volume is 300 centimeters cubed. I also know that the volume of my can is pi r squared h. And then I'm going to work towards making an equation. So the equation that I'm trying to restrict is the cost. In order to find the cost, I would need to multiply the cost of materials times the amount of materials used. So I'm going to use the surface area. So I do need to know the surface area for a cylinder, which is the area of the sides, 2 pi r h, plus the area of the top and bottom, those two circles. My cost is going to be 0.04 times the area of the sides plus the cost times the top and the bottom. Now what I can do here is I can expand a little bit. So I would get 0.08 pi RH. I'm just leaving the pi alone because it is just a number. Then I get 0.1 pi r squared. So now I need to use my constraint equation up here so that I can substitute and get my cost equation in terms of one variable. I notice that I only have one h, so I'm actually going to rearrange here for h. It's actually easier to rearrange for h anyway, but then I only have to make one substitution. So I'm going to take this value, substitute in for h, and then rewrite my cost equation in terms of one variable. So I've got r times 300 over pi r squared plus 0.1 pi r squared. I'm going to do some more simplification here. I can cross out pi r, pi, and an r. Multiplying those two together actually gives me 24 over r plus 0.1 pi r squared. This is the equation that I'm trying to optimize. Now that I have that, the next thing that I'm going to do is take the derivative and set it equal to 0. So a little bit trickier to take the derivative here. Just before I do that, I'm going to rewrite it with a negative exponent so that I can just apply the power rule. So my derivative is minus 24 r to the minus 2 plus 0.2 pi times r. So now what I want to do here is I want to be able to set this equal to 0. So that means that I want to solve this equation right here. In order to do that, I need to add the two terms on my right-hand side. I can do that by finding a common denominator, which means I have to multiply my second term by r squared over r squared. This is going to give me the expression 0 equals minus 24 plus 0.2 pi r squared, pi r cubed, over r squared. When I'm solving a rational equation like this, what I'm going to do is set the numerator equal to 0, because that is the only way that the equation can equal 0. One of the restrictions on a rational function is that the denominator can't equal 0. So the only way for me to make the left side of that equation equal to 0 is if the numerator is equal to 0. So this is something that I can solve by isolating r. I'm going to divide both sides by 0.2 times pi. And then I'm going to take the cube root. I can simplify a little bit. 24 divided by 0.2 is 120. Oops, no decimal. Over pi. And then I'm going to take the cube root of that answer. That is going to give me my potential minimum value for r. So let's verify that we actually do have a minimum. So for a minimum, my second derivative evaluated at root 3, 120 over pi, would have to be greater than 0. So my second derivative of the cost is going to be 48 r to the minus 3 plus 0.2 times pi. When I substitute in my value, root 3 of 120 over pi, it doesn't really matter what it is. The number that I'm substituting in is positive, so I'm just going to write it in here. I would have root 3, 120 over pi cubed plus 0.2 pi. I'm not concerned about the term at the end because there's no substitution there. That's already positive. And what I notice is that I'm cubing a positive number. So that is definitely going to give me a value that is greater than 0. Therefore, the r that I found does actually give a minimum. Now our step number 5, we should add that to our steps at the top, is to actually answer the question that's being asked. So I'm looking for the dimensions. I already have one, root 3, 120 divided by pi, and then I need to figure out what h is equal to. So I have my expression for h. I'll go back up a little bit. 300 divided by pi r squared. So I can substitute in my value for r. You should substitute in your exact value here. So 120 over pi all squared. And then when you evaluate that, you could round to 3 significant figures. So about 8.42 centimeters. If I were to do the same thing with my r value, I would get 3.37 centimeters. So therefore, the dimensions that minimize the cost are r equals 3.37 centimeters and h, I'm running out of room down here, equals 8.42 centimeters. 2 examples of optimization using calculus.